This is a video created to accompany the music education research text by Miksza, Shaw, Richerme, Hash, and Hodges. In this video, we'll walk through how to use Spss to conduct analyses and produce plots for examining differences with interval or ratio level outcome variables similar to those presented in the Determining Differences with Inferential Statistics chapter of our text. We'll use the file labeled Differences Chapter Scalar Data.sav, which was created to accompany this chapter and is available among the online supplemental materials for our book. Our first example involves a hypothetical scenario in which we want to examine children's rhythm perception test scores as a function of whether they experience an experimental dance curriculum or a control condition. We can use the chart builder function found in the Graphs drop-down menu to create box plots to visualize the data for this example. If we go to Graphs to Chart Builder, then we can select Box Plot, drag that into the empty field, and we'll have our two category nominal variables, our x-axis variable, and our rhythm perception post-test as our y-axis variable, and we can click OK. And you see generally it looks like the children in the dance group overall and on average performed better than the children in the control group on the rhythm perception post-test. Since different individuals were randomly assigned to one of the two groups in this scenario, we could consider the scores from the two groups to be independent of each other. Therefore, the independent samples t-test is the appropriate test to use with these data. To conduct this analysis, navigate to Analyze to compare means, and then select Independent Samples t-test. Then we can enter Rhythm Perception Post-Test as our test variable, and Experimental Group 2 category as our grouping variable. We also have to define the labels for the grouping variable. In order to make things a bit more intuitive, I'm going to switch the labels for group 1 and 2 to be 2 and 1. 2 represents the treatment group and 1 represents the control group. This way we're subtracting the control group from the treatment group and avoiding a negative number. And then we'll click Continue. Note that the Estimate Effect Sizes box is checked by default here, and we can click OK. We get a lot of information in the output for this analysis. We get summary statistics showing that we have 20 children in the dance group, 20 children in the control group, the means of each, the standard deviation of each, standard error. And then this beginning of the output for the independent samples t-test is actually a test of an assumption of this statistical procedure, which is that the variances, the dispersion around the mean for each group is relatively similar. The non-significant result means that we've met that assumption. There's not a significant difference between their variances. Then we get down to what we're really interested in, the t-value, the degrees of freedom, and the two-sided p-value, the significance level of this test. And we see that that is less than 0.001. That means we can reject the null hypothesis of no difference between these groups, since this p-value is much lower than the typical criterion of 0.05. We also get just a description of the difference between these means, which is subtracting 60 minus 47 here, and then the 95% confidence interval of the difference between means, the lower limit and the upper limit. Last, the effect size shows up. There's 3 different versions we could use. Cohen's D and Hedges G are quite often used in music education research. We'll stick with Cohen's D, and a Cohen's D of 1.144 means that this was a large effect size. In other words, the distance between these two means was more than 1 standard deviation unit. A Cohen's D greater than 1. Next, we consider a hypothetical scenario in which we want to examine children's rhythm perception test scores at the end of the experiment to their scores 6 months later. I'm going to close this window since we don't need it anymore. In this next scenario, we're examining the scores from the same group of participants on 2 occasions. Therefore, we would consider the scores from these 2 occasions as related in some sense or dependent on each other in some way. So we describe the scores as coming from dependent samples or paired samples rather than independent samples. We can visualize these data in Spss with bar or line charts. Let's use the chart builder function from the Graphs menu to create bar charts. So we can go Graphs to Chart Builder, going to reset from our previous settings, choose bar as the chart type, put that into the empty field. Then we can enter rhythm perception post-test and rhythm perception 6-month follow-up, one after each other, into the y-axis. There's the post-test variable. And now watch what happens when I enter the next in the same axis. A little plus button shows up. And then Spss gives us a dialog box that basically tells us it's creating a grouping to represent the changes over time. So we'll click OK. We can also ask SPSS to show the 95% confidence interval of our means to get a sense of the variability in the data. And we'll do that by clicking the display error bars here. And now we can click OK to produce the plot. And so a bar plot, when we're dealing with groups and means, indicates the height of the bar indicates the mean of the group. And so we see the mean 6 months after was higher than the mean immediately at the post-test for these 60 children. And the little brackets here represent the lower limit and the upper limit of the 95% confidence interval for each mean. Sometimes bar plots can be deceiving because they may mask the variability in a group. In other words, the means are represented by the height of the bars, but there are also participants who had values above the means, which aren't represented on this chart. So box plots sometimes can be preferred to bar charts, but we'll use these here because they're a little bit more convenient to produce in SPSS. The dependent samples t-test is the appropriate test to use when comparing data from the same people on 2 measurement occasions. To conduct this analysis, we'll go to Analyze again to compare means again, but this time we'll choose Paired Samples t-test, which is the SPSS terminology for dependent samples t-test. To conduct this test, we need to enter our 2 variables together as a group. So I'll select the 6 months follow-up variable and the post-test variable and press Shift while selecting them so that I get both at the same time, and then enter them in as a pair of variables. Notice again that the estimate effect sizes is checked by default. That's all we need to do. We can click OK. And again, we get a good deal of information here. We get descriptive statistics. Notice that there are 60 children represented in each of these measurement occasions. It's the same 60 children, right, measured at different points in time. SPSS also gives us by default the correlation between these 2 measures. And then we get the information we're really interested in, the difference between the means, the standard deviation of the difference, the standard error of that, the confidence interval of the difference between the means, the t-value for our test and the degrees of freedom, and then again the 2-sided p-value or significance level, which is much lower than 0.05, our threshold for statistical significance. So once again, we can reject the null hypothesis of 0 difference between these measurement occasions. The effect size estimate down here of Cohen's d is 0.84, which is indicative of again a large effect. So I'm going to close this window since we don't need it anymore. As discussed in our book, different statistical tests are necessary when comparing more than 2 groups on a scalar outcome variable. The analysis of variance, otherwise known as Anova, is the most commonly used family of procedures for such analyses. Let's consider the example in which we'd like to compare the rhythm perception post-test scores of 3 groups of children, a control group, an experimental dance group, and an experimental free movement group. We can again visualize these data with various types of plots, and let's use box plots as we did with the 2-group example. So again, I'll move from Graphs to Chart Builder, reset from our previous analyses, select box plot and draw that into the empty field. And this time I'm going to select the 3 category nominal variables, our x-axis variable. And again, rhythm perception post-test is our y-axis variable. And then select OK. And so now we can see that there is a difference between the control, apparently there's a difference between the control group and the dance group, and probably between the control group and the free movement group, but maybe not between the dance and the free movement group, right? And we can see all 3 groups that are in our hypothetical example demonstrated there. And again, the box plot is convenient because it shows us variability around the scores, not just the height of a bar, which indicates a mean in a bar chart. Since different individuals are randomly assigned to one of the 3 groups in this scenario, we would consider the scores from the 3 groups to be independent of each other. Therefore, the one-way ANOVA is the appropriate test to use with these data. To conduct this analysis, we navigate to Analyze to compare means and select one-way ANOVA. Analyze, compare means, one-way ANOVA. Then we can enter rhythm perception post-test as the dependent variable, or put it into the dependent list, as SPSS indicates here. An experimental group 3 category is the grouping variable, or what SPSS refers to as the factor variable. Note here that we need to check the estimate effect size box, whereas we didn't have to do that before when we were analyzing using the t-tests. Also, since Anova results will only tell us if there is a significant difference in the outcome variable according to the grouping in general or not, in other words, it'll produce an omnibus test, we can also go a step further and request a post-hoc test from SPSS to further examine whether significant differences exist between pairings of the groups. If we click on the post-hoc menu, you can see there are many options here, and we can choose the method we describe in our text, which is Tukey's method, and then click Continue. That's all we need for now, so we can click OK. So again, we get a good deal of information. First, the Anova test results, in which we see sums of squares, degrees of freedom, mean squares, all information that is used to compute the F statistic for determining whether there is a difference in rhythm perception scores as a function of groups. And we see from our p-value, our significance value, that again, we would reject the null hypothesis of no difference due to groups because this value is sufficiently small, much lower than the 0.05 threshold for significance traditionally. Our effect size indicator for Anova is the eta squared value, which here is 0.26, and you can see the 95% confidence interval for that value as well. 0.26 means that the proportion of variation in the rhythm perception post-test scores that can be explained by the grouping, the three groups, is 0.26. In other words, 26% of the variation in rhythm perception post-test scores can be explained by the grouping. That's interesting, of course. We know now that there's a difference due to grouping, but we don't know where the differences are in terms of pairs of groups. So we go further to look at our post-hoc sub tests to see where those differences might be. And you see in this box, we have multiple comparisons. The comparisons of the control group with the dance group is significant. The comparison of the control group with the free movement group is significant. However, the comparison between the dance group and the free movement group is non-significant. So, as we suspected when looking at the plot, the pairing of control and dance is a significant difference. Dance has yielded significantly higher post-test scores. The pairing of control and free movement is significantly different. So we can note that free movement led to significantly higher post-test scores than control, but there's no difference significantly, statistically, between dance and free movement. I'm going to exit out of this output since we don't need it anymore. And for our final example in this video, let's consider a situation in which we want to compare the same group of participants across more than 2 measurement occasions. As with our previous example of 2 measurement occasions, we can visualize these data in SPSS with bar or line charts. So we'll use the chart builder function from the graphs menu to create bar charts. So again, graphs to chart builder, and I'll reset from our previous settings. We'll choose the type of plot, a bar chart. And now we'll include rhythm perception post-test, but also rhythm perception 6-month follow-up. You see the plus sign show up, and then SPSS again tells us it's creating a grouping variable for time. And now we'll add a third one in there as well. So now we have 3 time points. And again, we'll ask for error bars that represent the confidence intervals to give us a sense of the variability in the groups or in the data. If we click OK, we see our 3 bars representing means, the height of the bar representing means at post-test, a higher mean at 6 months follow-up, and a higher mean at a year follow-up, and then the black brackets representing confidence intervals, the lower limit and the upper limit of the confidence intervals. So to test for significant differences among the means for these 3 measurement occasions, we can use what's referred to as the repeated measures ANOVA. For this analysis, we need to go to different menus. We navigate to Analyze, to General Linear Model, and then to Repeated Measures. Next, we have to define our repeated outcome, which SPSS calls a within subjects factor. So we can call our factor measurement occasion, since that's what our 3 variables represent. And since we have 3 measurement occasions, we'll input 3 as the number of levels, then click Add, and we'll click Define so we can move on to the next step. Now we can enter the variables representing our 3 measurement occasions into the fields waiting for them. So rhythm perception post-test, 6-month follow-up, 1-year follow-up. I selected them using the shift key, and then I'm putting them into this slot here. We need to click on Options to find the box to check to return the effect size appropriate for this analysis. Again, it's not something that is checked by default. So under Options, we can click Estimates of Effect Size and click Continue. Again, since the Anova results will only tell us if there's a significant difference according to the measurement occasion overall, we can also request that SPSS further examine whether significant differences exist between pairings of measurement occasions. If we click on the EM means box, which stands for estimated marginal means, we can ask SPSS to compare the main effects of measurement occasion. So I'll slide this over here, compare main effects, and we'll apply the Bonferroni correction procedure so that it adjusts for potentially inflated type 1 error due to multiple comparisons. We'll click Continue. And that's all we need to do now, so we'll click OK. Again, we get a lot of information. First, SPSS tells us that our outcome is rhythm perception, and it has 3 measurement occasions. It gives us a multivariate test, which is another option for interpreting repeated measures analyses, but we'll ignore that. It gives us a test of the assumption of sphericity, which we only very quickly in a footnote describe in the book. What is interesting to note here is that, and to keep in mind, is that with repeated measures ANOVA, when you have more than 2 measurement occasions, you almost always end up in a situation where you do not meet the assumption of sphericity. Holding aside for the moment what that means, that is the case here in this analysis. We see there's a 0.005 for the Mauchly's test of sphericity, meaning it's significant, meaning we do not pass that assumption. And so because of that, we refer to a line in the output for our within subject effect. This is the main box of output that we're really interested in first. We'll refer to a line that adjusts for the violation of sphericity. And the method that is commonly reported in music education research is the greenhouse Geyser method. So note that there are 1, 2, 3, 4 lines for each of these sections of this chart here. We'll only look at the line that corresponds with greenhouse Geyser, and that would be the line we would use to produce a table, let's say, too, like the one we included in our text. So in this output here, we see the omnibus test following greenhouse Geyser. We get sum of squares, degrees of freedom, mean squares, the F value, and then the sum of squares, degrees of freedom, mean squares for the error term. And again, the p-value, or the significance value, is 0.001, which is much lower than the threshold for statistical significance, traditionally of 0.05. So we can reject the null hypothesis of no difference due to measurement occasion. There is a difference among these 3 occasions. The effect size indicator here is, again, eta squared, but it's called partial eta squared due to the mathematics of this procedure being different than the previous ANOVA we ran. But we would interpret it in a similar way. So we could say that 48% of the variation in rhythm perception scores is due to measurement occasion, which is quite a lot of variation. And so within subjects contrasts is something that is produced automatically with SPSS. We're not interested in that right now, or for the analyses discussed in our book. The test of between subjects effect is something that is mathematically necessary to produce our outcome, but we don't have a between subjects factor. We only have 3 measurement occasions here, so we can ignore that. And now we see the extra comparisons we asked. So we have the means of the 3 measurement occasions, the confidence intervals for each measurement occasion, which would be depicted by the brackets in the chart we produced. And then the pairwise comparison. So measurement occasion 1, the post-test, to measurement occasion 2, 6 months after. And there's a significant difference between measurement occasion 1 and 2, according to the p-value being less than 0.001. And then the comparison of measurement occasion 1 to measurement occasion 3, and that's significant. And then in the next row down, we can see that measurement occasion 2 and measurement occasion 3 is also significant. So all 3 of the comparisons that are possible here, 1 and 2, 2 and 3, 1 and 3, represent significant differences. So we could say that the rhythm perception scores increase significantly with each occasion over time. We hope you found this video helpful, and again, thank you very much.